Hello and welcome to the STM32CubeMX training. What I'm going to show today is how to use the STM32Cube and what features you have and what is the best way to use it. So first of all, let me introduce the options that you have on the cube. Right on the top you have File, and then you can create a new project or load previous project. Under recent projects, there are projects that you did before. Under the project, now it's grayed out because we don't have a project, so we can't generate anything. Under window there's the output, and under help we can see the help files of the cube, and when we can check for updates and install new libraries. This is one of the things you have to do immediately after installing this STM32Cube by going into help, install new libraries, and then you can see what are the options that you have already installed and what are the options that you can install. After pressing check, the system goes through a quick check, and as you can see I have the latest software. If something is not installed, you can see that it's missing. It doesn't have a green button. And you can add or remove just by clicking the option. So for example, I have the STM32CubeF7. If I want to remove it, I just click on it and then I do remove now, and it will uninstall it. For our case uses today, we'll try the STM32CubeL0 release. As you can see, I have the latest versions to the current date and the previous version that I can remove by just clicking and removing the files. I won't do it now, so we can continue with our presentation. Under the tabs, under the options, we have create new projects, load a project just like in the file, and other options that are not available now just because we don't have a project. So let's start with a new project and see what we can do. So let's start with a new project. So by clicking new project, we're having a new window. This window is built out of two tabs under MCU selector and board selector. We'll start with the board selector because that's the easier option. Under vendor we can see ST microelectronics. Under type of board we can see the different type of boards that are available today, if it's the Nucleo 144 or the 32 or the 64, or the Discovery board or the EVIL board, the big ST boards. And under ST we can see all the types of ST demo boards. For today's example we'll choose the L0. So going to the MCU series, we can see the different types of microcontrollers that the ST has, and we can choose the STM32L0, and then we can see all the available demo boards of the Nucleo. On the left side we can see the peripheral selection, and depending on the microcontroller that we're choosing, we can see all the available peripherals that we can choose out of any one of those boards. And for this example we'll take the Nucleo 64, the Nucleo L053R8, and if we click OK, it takes a few seconds, and then we can see the microcontroller with all the peripherals that are already set on the Nucleo. Let's go ahead, and this time we'll open a new project, but this time we'll choose the device depending on the product. So it's the same window. Under new project we have board selector and MCU selector. This time we'll try to find the different MCUs depending on the peripherals. So for example, if we want to see 5 pins with ADC 12-bit, so we just write number, and we can decide 5 out of 40. If we want, for example, USB full speed or USB device. And as you can see, when I'm choosing the peripherals, the list changes depending on what I'm choosing. If I want, for example, segment LCD, again, it changes and it shows me all the information or all the devices that are available for my selection. For this example, we'll choose the STM32C-L053R8, and if you'll see, it's the same device that we have on the Nucleo 64. So I chose the device and I'll click OK. But this one is a BGA, and you can see immediately, I can see it on the screen, and this is not the device I want to. What we can do, at the bottom of the screen, we can see that there is a full list of devices, and all of them are aligned with the required peripherals that I've set. So I can quickly change it if I chose the wrong package, for example. So if I'll go here, and then I can choose the L053R8TX, and that's LQFP64. If I double click, I can see the package that I chose before. This window now has more options available because I've chosen the product. And let's see what other options we have in this. So let's see what other options we have in this window. So under project, we have generate code, generate reported settings. I'll show it in a later stage when we'll generate the code and the report for this project. For pinout, we have clear pinout, clear signal mapping signals, set unused GPIOs. So we can set all the free GPIOs that we have in at the end of the project. Generate CSV pinout text file if we want to send it to someone. Collapse all, disable modes, expand all. That's all the peripherals on the left side. Zoom in, best fit, and zoom out. To zoom in and out, we just roll the mouse wheel back and forth. If we hold the left button mouse, we can move the part left and right, and we can zoom in and out again with the wheel. Under the options here, we have quick buttons, and most of them are just the same. Import project, it's available with the default configuration. Save current project or save as, generate report, keep current signals placement. This option, because the STM32 has alternate functions, this option is set. You can see a pop-up balloon. Options will not be able to move to alternate functions. So if there is any function that can be, for example, like the UART, can be at 2 different pins, when this is set, the software will not, the CubeMX will not change the pinouts to the alternate functions to have maximum flexibility. This is the reason why it's best, at least in the beginning, to have this unchecked, and when you finish the project you can set it, and then the CubeMX will not move the pins, and then you won't have any problems when you're regenerating the code if you need to do any changes. This is undo and do. Collapse all IPs, disable all. This window, you can find any pin that you're looking for. Just type it, for example PA9, and then you can see all the PA9 flashing when you're looking. This is a simple device, but when you have like 217 pins, it's really difficult to search for them. This is a really quick way to find them. Also, you can do it by a port if you want to see how a port is mapped on the microcontroller. Zoom in, out, use the labels. I'll show it in a different later stage. And help. The middleware, and you have the peripherals. So under the tabs you have the pinout. This is the first thing that we need to do, and we need to configure. After we'll finish configuring the device, we'll go to the clock configure. The clock configure depends on the pinout, so anything that's grayed out now will be enabled depending on our pinout configuration. For example, the external oscillator, now it's disabled because it's grayed out, and after we set it in the pinout, this will be enabled. After we finish the clock configuration, we'll go to configuration. After setting all the configuration, again, this window is also dependent on the pinout and the clock configuration. We'll set all the peripherals and all the settings that we need, and then we'll generate the code. The last tab, the only dependencies that it has to the pinout is when we make the power consumption calculation, and I'll show this also in a later video. So coming back to the pinout, the middleware is partly dependent on the pinout. As you can see, our device has a USB function, but the USB function is grayed out, and this is again because we didn't set the USB yet. It's dependent on the peripheral. A free RTOS doesn't depend on any peripheral, so we can add it or disable it. And the FAT file system, again, it's a user defined depending on what we're doing. Anything that we set, it becomes green. So a green color means that we set the peripheral or the middleware as an on or available. The best way to use the peripherals in the ST is always use things that are most important, like USB, UARTs, low power UART, or low power timers, or LCD, and only at the end use the peripherals that are not so important, for example ADC or simple GPIOs in and out. So in our case, if we want to add one of the USB devices, as I said, it's most important to start with the important peripherals. So let's take the USB, click V on the device full speed, and immediately we can see two pins are set as USB D plus and the D minus. Those pins are set for this peripheral. Another thing we can see is that we have a small yellow exclamation mark, and if we open it, we can see that under group 4 we have another exclamation mark, and if we open it even further, some of the options are yellow, some of the options don't have any marks, and some of them are red. The difference are as follows. The red means that I'm not able to use any of those functions. If we put the mouse and hover over the red, we can see that the CubeMX tells me what are the CubeMX tells me what are the errors and what pins are in conflict with those pins. We can see that the USB device full speed is with conflict with G4 IO3. On the yellow, it means that some of the options are available and some of the options are in conflict. As you can see, G4 IO1 and G4 IO2 are available, but G4 IO3 and 4 are not available. It's the same thing with the shield. 2 pins are available, 2 pins are in conflict. The next thing that I want to choose is the low power UART, and we can choose, for example, the asynchronous. Again, as before, 2 pins are immediately set, and we can see that they receive the name of low power UART RX and low power UART TX. At this stage, we can change the name of the low power pinouts. At this stage, we can fix the names of the pins that were given by the STM32CubeMX. For example, if you want to change the TX name, we right click on the mouse and then we left click on the mouse and then we give it a name, for example GPS underscore TX. All the names have to be full names without any spaces, because those names can be used after that while writing the code. So after giving the name, we click enter and the name has changed. We'll do the same thing for the other pin. We stand on the pin, right click, left click, GPS underscore RX, enter, and we've changed the name of the pins. Few things that are very important when doing a project on STM32Cube. The most important part is the sys peripheral. The sys peripheral has the serial while debug. As you can see, as a default, this option is not ticked. And one of the most important things when building a project is to have this option ticked. When you do this, two pins are available or being used. One is the system clock and the other one SWD pin PA13 and PA14. If you don't do this, after programming, those pins will become GPIOs and you will not be able to communicate with the device unless you use the ST-Link to erase the device and then communicate back again. So this is one of the options that are very important to keep in mind, and if you have any issues connecting to the device, this is one of the options that you need to check after generating the code. Other options is system wake up. Those are other pins that you can be used to wake up the system from stop mode. VRFID ADC connection. Power voltage detector, if you want to detect what is the voltage of the device and to set it under configuration. And time-based source, is it SysTick or any one of the timers. So really quickly, I'll set a few more peripherals just for to see how it's being done. As you can see, I've chosen UART 1, and now a few things are disabled because it's a conflict with the USB. As you can see, I just hover with the device and we can see what options are available and what options are disabled. This is the real-time clock. In the real-time clock, I have two different alarms. I can set it as internal alarm or routed to out. As you can see, if I do routed to out, it opens a pin to PC13, and this can be used, for example, if you have a DC to DC with an enable pin, you can shut down the whole system, and then when you have an alarm to wake up the device, it will enable the DC to DC and will power up the whole system automatically. You have alarm B, again, wake up. This is routed because the routed pin is already set. You cannot do it again, and you can do internal wake up. Tamper pins, as you can see, those are tamper pins. This is part of the STM32 device. When you connect those tamper pins into switches, and you can put them inside your box, and when someone opens the box, you can set how the device will react. Do you want to erase the flash? Do you want to put a timestamp? And other different things that you want to do when you see that someone tampered with your product. Reference clock detection. If you want to have a reference clock in. Other things that you have, RCC, those are the oscillator. You have high-speed clock. If you want to use a bypass clock, you have only one pin, so it's an oscillator in. If you want to have a crystal, it's 2 pins. The same thing with the low-speed external device. So you have high-speed external and low-speed external. I2C. At this stage, I want to show you another feature that the STM32 has, and the CubeMX. This function, as I said before, the STM32 has alternate functions. Because we didn't set the keep current signals in placement, the STM32 Cube can move the pins to different locations while setting the peripherals. One of the things we can do is we can set the peripherals manually. If we want to set or move any peripherals to a different alternate functions, what we do is click and hold the control button on the keyboard and pressing the left button of the mouse on the pin that we want to move. And as we can see, when I click on PB7, PB9 highlights. If I click on PB6, we can see the PB8 highlights. Now there are 2 ways to move the pin. One way is to left click on PB9 and move it manually. I2C1 SDA. I'll go back. The other way is while holding the control and holding the left button of the mouse, we can drag the pin and bring it to PB9. Those are the 2 available options. The difference between pins now is that PB6 doesn't have a pin stuck into it and PB9 has a pin stuck into it. The reason is because we have changed the PB9 pin manually and we moved it and we have copied it to a different location. So anything that has a pin into the pin means that we changed it manually. So you can really quickly see what was configured by the CubeMX and what was configured manually. We can try and do it for the SPI. As you can see, PB14 highlights. We can do it to PC3. We can do it to the UR2, but this time it's being held by the syst, and also this one is being held by timer 2, so we won't move them there. We can turn on the dock. We can turn on the comparators, for example. We can go on. If we want any ADC pins, you can see some of them are already disabled and we cannot use them. This is again the fact why I've highlighted that it's very important to use the most important peripherals first, and then at the end decide on the simple peripherals or the simple pins as GPIO in and out or ADCs. Now we can decide on using some of the ADCs, and if we want any GPIOs, we need to do it manually. For example, PA8, we left click on the mouse and we can decide on what options we want to have the pin as a GPIO input, output, GPIO analog, event out, or GPIO with interrupt. So I'll do GPIO input, GPIO output, and GPIO output. As you can see, those 3 pins have a pin in them because I manually configured them. Because we have decided on using the USB, the middleware is now available on the USB device. So after opening the middleware for USB device, we can see that we have different options for the USB middleware. We can do audio device class, communication device class, virtual COM port, download firmware upgrade, it's a DFU, human interface device, HID, custom human interface device, or mass storage class. For this example, we'll just take the communication device class as a virtual COM port. Now we move on to the clock configuration. As you can see immediately in the clock configuration, we have few red highlighted peripherals. For example, the USB clock that is required to be 48 MHz and the APB1 peripheral clocks. Because the system automatically shows us that there is wrong configuration, and you can see it also on the tab, it asks me if I want to have this issue resolved automatically. If I click yes, the system goes through different settings and try to find the best way for the clock configuration. For this example, I'll show also how the clock configuration works. As you can see, more options are available than before, and we'll start from the top left and move down and explain each section by section. You can see that the low speed external clock is set and it's in blue and not gray as before, and I can change the different settings for what type of input I want for the real-time clock. I can either use the accurate low speed external device, or I can use the low speed internal that has 37 kHz. I can also use the high speed external and use a divider to try to get to the minimum settings, but again it's too high because I'm using a 8 MHz. The other options that I have are high speed external. This can be set from 1 to 24 MHz depending on the device. I can set this manually, or I can use the internal 16 MHz clock. Again, when the system sees that I have set it in the wrong way, it gives me all the problems and what peripherals having a problem with the clock that I've set. If I hover on any of the red, it explains to me why the system clock frequency is not set correctly depending on the peripheral. You can see, for example, the USB clock needs to be between 47.88 MHz to 48.12 MHz. There are a few options to correct this. You saw that the first time it was made automatically, and I can resolve this automatically again by using this button, Resolve Clocks Issues, or I can try to set this manually. If I click, for example, back again on the high speed external, and let me change something here so we can see that there is a problem with few places. Okay, so the USB clock is really low. I can change the clock to 48 MHz, and if I click enter, again the system will fix everything. I can also do other things for the system and configure the clocks automatically. For example, if I want the system, the peripheral and the system to run at a much lower clock, I can set it, for example, to 8 MHz. And the system again tries to find the best configuration. And it said it cannot because any lower than that, it won't work with the base settings. But I can, for example, lock this, and what would happen now if I'll change the settings, the system will try to fix it depending on what I've set. If it manages. So there are different ways to play with the clock system and try to reach the best options for the system while preserving everything. Here is another example that we have, for example, a clock out, but it's grayed out. In order for us to have it enabled, we need to go back to pinout, and under RCC we have master clock output. And if we go back to clock configuration, now we can see that this option is available, and we can output one of the internal clocks into the MCO pinout. For example, low speed external, we get a 32 kHz, low speed internal, high speed external, that's a 4 megahertz, high speed internal, that's a 16 megahertz, the PLL clock that we get a 24, system clock that we have again 24, 6 o'clock, multi-sys internal clock, and high speed internal. The MSI RC can be configured to different speeds, as you can see here. Now move on to configuration. Under configuration tab, as you can see, we have immediately a red X. That means that one of the peripherals has a problem, or more than one of the peripherals. All the other peripherals, you can see that there is a green tick. It means that everything is fine. And if we go to the comparator, it says please select a negative input source in the pinout view. So in order to do that, we have to go back to the pinout, to comparator 1, input, and decide on the DAC out or internal VREF. If we do that, the X mark is gone and everything is set as green. On the left side we can see the middleware and we can see the peripherals, and again we can see all the different pinouts and the functions that we have set. The main window is divided into a few sections. We have the peripherals under System, Connectivity, Analog, Control, and Multimedia that we don't have at this time. And in the middleware we have only the USB device. If we go back to the pinout and we add FreeRTOS, we can see under the configuration that we have in the middleware also the FreeRTOS. So let's go slowly depending on the peripheral, and we go on the different options that we have. In the control we have the real-time clock. Under most of the windows we have parameter settings, user constants, NVIC, interrupt settings, and GPIO settings. For the parameter settings, this is independent for every peripheral, the different functions that you have. For example, for the real-time clock we have hour format, if it's 24 or 12, asynchronous pre-divider value, and synchronous pre-divider value. Depending on the clocks, the information and the values that you can put in will be different and will be shown here. If you want to check other values, you'll have to go through by yourself and use the reference manual in order to find what are the best settings for your project. Under NVIC, if we want to use an interrupt, again we can enable it here, and under GPIO settings we can see all the GPIOs that the real-time queue uses and what are the available options for the pins. For timer, again, almost the same settings. So we have parameter settings, user constants, NVIC, DMA settings, and GPIO settings. For this peripheral, because it's a timer, we can use DMA. We have another tab of the DMA settings, and I will show it at a later stage. For the parameter settings, again, depending on the device and the clock configuration, we can set different values and different functions. Again, please refer to the reference menu of the device to find out what are the best settings. Timer 6, again, the same window with different functions depending on the peripheral. For ADC, you have different functions and different availabilities, what type of clock prescaler you want to use, how many bit of resolution, data alignment, scan direction, continuous conversion mode, and other options that you have. Interrupt, DMA, and GPIO. Comparator, trigger mode, output priority. For the DAC, output buffer, trigger. I2C, if you want to use standard mode, fast mode, or fast mode plus. And what are the speed that you want to use. With fast mode plus, you can reach from 1 kHz up to 1000 kHz. That's 1 mega. Rise time, fall time, depending on the device that you want to use. Analog filter, and clock stretching and other options. Low power UART, again, the baud rate that you can set. And parity and stop bits and all the other functions. For this example, I want to show, because most of the people are using UART, it is very important the speed of the communication. As you can see now, the baud rate must be between 2.93 kilobits up to 4 megabits. But if I go back to the clock configuration and I'll change the speed of the peripherals, for example, if I move this to 1 megahertz, I can do this by changing this to HSE, divide this by 4, and then fix this peripheral. I'm not able to because it requires 10 megahertz, but only for this presentation. I'll go back to configuration, low power UART. If I stand on the baud rate, you can see that the baud rate now changed from 245 bits to 333 kilobits. And that's again changes depending on the clock configuration. Now, after I fixed it again to 32 megahertz, I'll go back to clock configuration, low power UART, baud rate, and we can see now it can work between 7 to 10 megabits. Again, everything depending on the peripheral and the clock configuration. The rest of the peripherals are the same. For example, the SPI, UART, and USB. Again, depending on the speed and the rest of the functions. For system, I can configure the RCC and that's the voltage that I'm using. Is it buffer cache, prefetch, RCC parameters, and other configuration that I can use. For NVIC, this shows me all the peripherals and the interrupts that I have and what I've configured as external interrupt or internal interrupts. Again, all those pins are set for every peripherals. For example, the ADC, if I go to NVIC, I can see it here. I can click V, click OK, and if I go back to the NVIC here, I'll see it highlighted here. If I'll remove it here, it will be removed also from the ADC peripheral. For DMA, I can see all the DMAs that were set depending on peripherals. I can add them here, or I can change them wherever I've set. For example, I can add the DMA for ADC, and this is DMA channel 1, peripheral to memory and low. The DMA request settings is normal or circular, so I can have a circular buffer or a normal buffer. I can increment the address of the peripherals, or I can increment the address of the memory. For example, if I have the same ADC reading over and over again, I can increment the memory on where I'm storing the data itself. Data width, if it's half word, byte, or word, and for example here for the memory. If I want to add another DMA request, I can click add and click, for example, for the UART receive. DMA 1, channel 3, peripheral to memory, priority low, and depending on the buffer that I want to use. So at this stage I did peripheral to memory. I can do memory to memory also if I want to move different buffers in different locations. And again, if I click under the UART 1, I can see the DMA that was set in the other window. For GPIO, I can see all the GPIOs that were set for the different peripherals. In every GPIO, we have different settings. We can see the GPIO mode is alternate function open drain because this is a I2C. I can have pull-ups for the pins, so I can set it as internal pull-up, and I don't need external pull-ups for the I2C, or new pull-ups and then add an external pull-ups. Maximum high output speed. This is for how fast I want the transition of the signal on the I/O pin, if it's a fast mode, and if it's a user label. If I go to the low power UART, I can see that the user label is set here, as we done before in the pinout. After we finish with all the peripherals, we can go up to the middleware. In this case, I'll show the USB and the FreeRTOS. For the USB, we have different configurations. We can set the USB max number of interfaces. We can set the number of configurations. We can set other options like the maximize descriptors, user string descriptors, self power, USB debug level, and the CDC interval. We can set also the device descriptors. This is how the system, when it interfaces to the PC, this is what you see on the virtual COM port. So you can change the name to whatever you want, and you can change other settings. In the FreeRTOS middleware, we have more parameters to set. This is because this is the FreeRTOS. We can change the user preemption. We can change the tick rate in hertz. We can change the maximum priorities, and we can change many other options. After we've finished all the pinout file configuration and configuration. Now we can generate the code. Configuration under project. Now we can generate the code. We start first with the settings. Under the project name, we give the project its name. We put the project location and the tool change folder location. We decide on what type of tool change we want to use. Is it IAR, Kyle, True Studio, SW4S for STM32, and other tool chains. If we want to change the linker settings for the maximum heap size, we can do that here. Other important things to choose before generating the code is the firmware library package. In this option, we copy all the libraries into the project folder, and this makes a very big project. We copy only the necessary library files depending on the pinout and peripherals that we chose, or we add the necessary library file reference to the toolchain project configuration file depending on the toolchain that you're using. To generate files, you can either generate peripherals initialization as a pair, or have it all in the same file, as in this case. Backup previous generated files. Keep user code when you're regenerating new code. Delete previous generated files, so you don't have a clutter of too many files. And the health settings. This is an important function that is not set as a default, and that is set all 3 pins as analog. In the system, as you can see, we have some pins that were left untouched. Those pins are floating. This option just set all of them as input, analog input, so those pins will be set as analog and we won't have any current leakage. Under advanced settings, we can see the generated function calls. So we can see the rank, we can see the function name, and we can see the IP interface name and not to be generated. So we can change the settings. After setting all the information, we click OK, and now we can go project and generate code. When the system finished generating all the code, it will ask me if I want to open folder, open the project, or close this. This ends this STM32CubeMX. I hope you enjoyed it. In other videos, I'll show different examples on how to start the project and how to do different things with the STM32.